Welcome. We now have a look at circular motion. Now, circular motion, as the name suggests, is motion in a circle. And that means the study of this is important because we can look at many objects which actually move in a circle, all the way from planets going around the sun, something like the Earth, there's the sun in the centre, and the Earth moves around a big circle. Not exactly a full circle, but close enough. And we can also have a look at, this could be a nucleus, and that would be an electron, and you have electrons moving around nuclei. So from very big to very, very small motions. As well as if I was turning my car as I go around a corner, parts of the actual turn are bits of arcs of circles. So this motion is not just for full circles, but also parts of circles as well. So it's important to be able to deal with the motion as we change direction. And as we change direction, we look at the circular motion as parts, little parts of these directional changes are approximated to circles. So let's have a look at a motion in a circle. Firstly, let's take a mass, and we'll just put a blob out here. That can be a planet, it could be an electron. Let's just make it a mass. And we're going to have that mass, this mass m, and it's going to be in kilograms, as we always do. It's not going to change speeds, therefore it's going to go around this circle at a constant velocity. But according to our understanding of Newton's first law of motion, it says that if it didn't have a force acting upon it, it would go in a straight line with an unchanged velocity. So if there was no force on this mass, then we would have the mass following this straight line. It would fly off at a tangent. And we have an expression for that, to go off at a tangent. But we do have a force acting. This force, every time that the actual mass moves, forces it in. Every time it moves, it forces it. So there must be something out here pushing the mass into the centre. So there's always a force pushing it inward. As we go around, a constant inward force. And this force must be pushing it towards the centre of the circle. We call this centre pushing force. We're going to give it a value. Let's get a nice colour. And it's going to be F with a C down the bottom, and that was going to say it's going to be directed towards the centre. So it's a centre seeking force. It seeks towards the centre. In Latin, that is centre speaking is centri, and to foot it into the centre is pedal. Okay? I'll just say pedal. Okay, so it's centripetal, or you want to pronounce it centripetal, it's up to you. So it's centripetal or centripetal force. So let's clear those notations and write that down. So FC is going to be called the centripetal force. And the centripetal force. Okay. So if we put our mass back on again, here's our mass, then it's as if there is a massive big force. It doesn't have to be a big force, just a single force that pulls it towards the centre of the circle. And that force is called the centripetal force. It doesn't make it go faster or slower, so it just, the speed doesn't change, so it still has a constant speed. So we call this the tangential velocity. And it becomes unchanged. And we understand this. If we're on the Earth, this is the Earth going around the Sun, then the Earth doesn't speed up or slow down. It just goes around at the same constant velocity each time. But what is happening is it's pulled towards the centre by something. And in this case, the big something is the centripetal force. And this centripetal force is created by gravity. So the centripetal force is created by something. So this doesn't exist as a true force. It is created or made, created by another type of force. And that other type of force could have been gravity. It could be the electrostatic force, as in the nucleus and electron. Or if we're going around a corner of a car on the road, it's the road friction that acts on our wheels to make us go around in a circle. Okay? So the centripetal force is created by another force, and so we just collect all these possible forces into one name. The centripetal force. If a force acts to make an object move in a circle, that force is called a centripetal force. That force could be made by gravity, electrostatics, friction, or whatever. It doesn't matter, it's still called the centripetal force. Right, now, that centripetal force has a value. We know it now exists, therefore, we know according to Newton's second law that force must equal ma, so a centripetal force must equal, F must equal ma, and this must be acceleration. So there must be a centripetal acceleration. So it's only accelerations that create forces, it's only forces that create acceleration. As long as they're unbalanced, that is always true. So what is the value of this centripetal acceleration? Well, AC equals, according to the formula, V squared on R. I'm not going to prove that value here. That is in your textbook for proof, if you'd like to work out what it is. So the centripetal acceleration is V squared on R. This gives us that centripetal force would be Fc equals mv squared on R. So if that's the truth, you just say it's F equals ma, that's F equals m, and this part here is A. We all remember that force is measured in newtons, velocity is measured in meters per second, mass in kilograms. What is the R? R is the radius of the circle of the circular motion. Okay. So we have a very simple formula that we can then work out the amount of push that an object must have to make it go towards that centre. Remember, this force does not make it go faster or slower, but it still accelerates. So this is an example of an acceleration that does not change its speed, but just changes direction. So this is, just write that down, Fc changes direction of an object, of mass, but not its speed. And remember that speed is called the tangential velocity. Okay, now to show you how real this force actually is, we are going to have a look at a video which is, if you've ever been on the ride at Luna Park in Sydney here, we have a ride called the Rotor. So I'll take a few moments just to talk that up. Okay. But as the rotor starts to spin, these people are standing on a floor. So they all are masses going in a circle, and that means that they will start to have, the wall is pushing them towards the centre. Now, obviously, they cannot be pushed towards the centre because it's spinning so fast that there's an action-reaction force that they are then pinned against the wall. The floor then falls. Okay, so have a look at that situation there. So the rotor, this is the person here, and there's the wall of the rotor. Here is the centre of the rotor, and this is the floor of the rotor. So the person looking from above, here is from above, this is that person's head, there is the centre, and they're going around like that, so they're looking down at this. As they go around, it's the wall that constantly pushes them towards the centre. Okay? Now, according to Newton's third law, for every action force, there must be an equal reaction force. Because the wall is pushing them inward, they would like to keep on going in a straight line. Remember, Newton's first law says that all objects want to go in a straight line. Because they want to go in a straight line like that, but the wall pushes them in, they feel that push in as a pinning of themselves against the wall. So they feel pushed against the wall. In older science textbooks, this used to be called the centrifugal force. It's only an apparent feeling. It's not a true force. It's just the action-reaction feeling that you get as you are pinned towards the wall. In reality, the only force that of any matter here is the wall pushing you in. And that wall pushes you in at your mass times the velocity that you are spinning at divided by the radius of the rotor itself. Okay? So we're going to go through and have a look at some problems now. So before we do that, let's have a look at the definition of centripetal acceleration as in our textbook. So the centripetal acceleration is the acceleration of an object. Remember, if we have an acceleration, that means we also have a force travelling in a circular path with constant speed. Now please notice that it is a constant speed in this. It is directed towards the centre of the circle. And we know that that value is v squared upon r. This is your worksheet for circular motion here. And we're going to be using this to work. I'm going to work through. I'll leave you to do the majority of it, but you can pause the video and answer the questions as we go. So it says the first one here is to use, let's get that up and ready, to use the Fc equaling mv squared on r to calculate the centripetal force of a mass of 5 kilograms travelling in a circular path of radius 2 with a tangential velocity of 4. So this question just gives you all the values. So we know here that that is 5 kilograms. This here is equal to 4 and r is equal to 2. Don't forget that that's a square, so this would have to be squared over here. Take a few moments, pause the video and complete that question. Right, welcome back. Now, that's quite an easy question. You can go to the solutions that are also on the website to make sure that you have got the right values there. This table here is going to force you to redo this equation over and over again. So don't forget that m should always be in kilograms, v needs to be in metres per second, and r is always in metres, and Fc is a force and it always must be in newtons. So when we're going down this here, we firstly find that we have tonnes in this position, so that 5.5 tonne is equal to 5,500 kilograms, so don't forget that one. We have kilometres and in this position, so remember to convert that to metres by multiplying by 1,000, also there. This is kilometres per hour. Kilometres per hour is not able to be used. It needs to be metres per second. And to convert, we multiply by the 5/18ths to get that into metres per second. Okay? And these are all in newtons. So remembering, you can either rearrange to find the value. So if you want to, in the first one, if you want to find r, you can either rearrange first. In other words, what I mean by that, if f equals mv squared on r, we could rearrange by swapping the f and c around. So r equals mv squared on f, and then we can just plug in the numbers. If we want to find mass over here, get m as the subject of the sentence, we get fr on v squared equals m, and then we just pop it in. So you can rearrange beforehand, or you can just substitute in and then just solve as an equation. So I want you to take a few moments and answer question 2. using that and check your answers with the solutions on the website. Okay, welcome back. This is an extended question, so it goes through. A car, firstly, is travelling at 30 metres. Circumference of the circle is obviously going to be given by c equals 2 pi r. So we'll use that to calculate the circumference of the circle. If we know that we go around a circle, just say that the circumference is 10 metres. That's not the answer to this, I'll just give you an example. And it happens in 5 seconds, then the distance travelled in the 5 seconds is 10 and the time is 5. So therefore, velocity or speed is distance over time, which is 10 over 5, which is 2 metres per second. In this question here, the car completes a circle in 5 seconds. Then we're going to work out what the velocity is by using this formula here. So we know that speed is equal to distance over time. So we can work out here its speed, which is its tangential velocity. So we can work out what v is for use in the formula for v squared on r. Don't forget, in a few moments, that is ton, so it has to be converted, and we're going to use it to work out the centrifugal force. Okay, D. Let's have a look at D. What is the minimum force of the car's tyres that must apply if the car successfully completes the circle? What it means by this is, if I take an arc, let's just have a road going down here. There's a road, and here is our car. Okay? Now, as the car travels across and around this road, it travels as part of an arc of a circle. Therefore, if it's travelling as part of an arc, there must be a force at all times directed into the centre of the motion. So it's been arrow. And this F is FC. What is it about the car? What part of the car must be pushing it? It can't be a giant imaginary giant pushing here with his hand as it goes around. So what is it that is pushing the car towards the centre? And the answer is the interaction between the tyre, is that tyre, spoken things on it, alloys or whatever you want to call them, okay, and the road. As, the road is normally black. So, as you travel around, you will turn the steering wheel, so here's our steering wheel, to say we have to turn it this way to turn in that direction. As it does, it will turn this wheel ever so slightly. So if we're looking from above, there's the car. The wheels start to turn, this is very much exaggerated, the front wheels turn like that. The back wheels, of course, remain in the same position, so like that. So this is looking for the car from on top, so this is looking straight down the car. There's you sitting behind the wheel. There's your wheel. Okay, there's your headlights. And there's your engine. You're very close to the engine, aren't you? Okay. So as the wheels turn, because they're no longer aligning with the car itself, they give a sideways push to the car. That sideways push becomes the centripetal force. This sideways push is determined by how much friction there is between the road surface and the car tyre. So if the car's tyres are worn or balding, or the road is slippery, then FC is reduced. If FC is reduced, then it can't actually go in a circle. If FC is disappearing, we know that the one thing that Newton's first law says, that this object will want to go in a straight line with unchanging velocity. And that means it will skid out and not complete the turn. And that's the reason why we have to, when we are doing our turns, slow down, because we need to slow our cars down to be underneath the frictional limit of our tyres and the road. And we often find signs on the side of our roads which tell us, very similar, black, that we have a sideways turn like that, and then underneath it, it will have a suggested, say, 15 kilometres per hour as a limit, saying it would be good if you turn this at 15 kilometres per hour because it's a very, very tight turn. Any faster than that, you might skid out and you won't completely turn, and you'll crash into maybe a tree over here. Okay? So safety always goes first. Now you've got that under our belt, we'll have a look at the question. The question says, what is the minimum force the tyres must apply if it's got to complete the circle? The minimum force would be the centripetal force. You can have more than that centripetal force. That means that you can do a tighter circle and you can reduce your pull on the wheel. So what the minimum force is would be the centripetal force. So it basically will be the same. Number 2, identify some reason the tyres might not be able to supply this force. So let's have a look at some of these possibilities. Centripetal force is governed by a few things. Let's go into black again. Firstly, the two main things is your velocity, and it's velocity squared. So when you square a number, it always gets massive very, very quickly. So if you're travelling at 3 metres per second, then it's just, then that value becomes 9. But if you're travelling at 20, that number becomes 400. There's only a 17 kilometres per hour increase, metres per second increase here, but there's a really large difference over here. So the first thing that is the big problem about having centripetal force is a small increase in velocity means you need quite a large increase in centripetal force. So one of the problems with turning around in your road would be that you are travelling too fast. You've got too big a velocity. So that's one thing that might be having a problem. So you're trying to do this at a too big a velocity, and therefore your tyres will not be able to give enough friction to turn you around the corner. That's the first one. The radius. It could be a really, really small, tight curve. The problem with this centripetal force formula is it's a fraction. If we reduce the size of the denominator of a fraction, we actually increase the overall size of the full fraction. So if this was, say, let's clear up some more space. So we got it. So if this was, say for instance, 10, if the radius was 10, then that becomes, and the top was, just say the top 100, then the overall fraction becomes 10. But if the this is reduced down, say, to 2, then the whole overall fraction becomes 50. So reducing this makes this number go up further and further. So the problem, another problem that could happen is that you are trying to do a very, very tight curve. So rather than having this more U-bend to tight curves. And if you do it with a high velocity, there's no way that you can actually get your tyres to go around. And lastly, what's another problem with this force is that it's going to be, the creation of this force here is by other mechanisms. As we said, it could be gravity, it could be electrostatics, and in this case, it's friction. So this friction is created by the road surface as well as the tyres themselves. The road surface could have oil on it. It could be icy. It could be that it's the tyres are worn because someone's not looking after their tyres and they have to be replaced so that the grooves on the tyres are not acting well enough. So it could be any of those problems. The one thing that I have not mentioned is M. M doesn't really change. This is the mass of the car. The mass of the car is not really changing as you go around the curve. Yes, it's using up a small amount of fuel, and converting that into carbon dioxide and water, but it's not significantly changing the actual force itself. Okay? So take a few moments now and go back to this one. Complete question 3. Right, welcome back. We'll have a look at the next part, which is period. When we move in a circle, let's get another up, and let's circle back. Let's go on. So let's just take a few minutes. Okay, here we are. When we have moving around a circle, we say that the time taken for it to do one complete revolution, so that's the time for that, is called a period. Now, so the period is, once again, if this was an electron, it would be the time taken to go around one loop, one full circle, one full revolution. We, however, have a name for when this is a planet. If it's a planet, a full revolution is called a year. So we know that the Earth's period is 365 days and a bit. If it's a moon, then we call that a month. So it's 1 month. So that's that, okay? So a period is defined as, this one here, is the time taken for a motion in a circle to complete one full revolution. Okay, so it's a time. So please realise that it's not anything to do with length. Got it up there, got it, one. So it's time taken for one revolution. And if it's a planet, it's a year. Okay. Now, let's just take the first one here. Complete the following table describing the mass travelling in a circle of a certain radius and velocity, period. So this is the time taken for going around in one full circle. This is the radius. We've got to work out the velocity. Velocity is distance over time. This is a circle. Don't forget the distance in a full circle is 2 pi r. And the time taken is t. So we use 2 pi r, so we use this here and we use 2 pi r. And this one over here as t, and we can work out the velocity. So we now can work out v here. After we found v, we now know the mass. Remember that has always been kilograms, so the next one down, please make sure it's converted. This is grams, so convert that to kilograms. We can then use the formula Fc equals mv squared on r. Okay, so in all these cases here, you have to use this formula first, v equals 2 pi r on t, to work out what all the other parts are. After you've done that, have a look at the solution, make sure you're right, and then you can move on to number 5. Okay, pause the video and do that now. Okay, let's start with 5 and 6. These are just compound questions using the whole things that we've learnt there. In all these cases here, we've got the mass. There's mass. This is the maximal frictional force, so that will be the maximum circular force. That's the maximum Fc. Remember, when we're talking about tyres in a car, the maximum frictional force will be the maximum centripetal force. So this becomes simply FC. And when that's the maximum FC, then that will be the highest velocity using this formula. So FC equals mv squared on r. Maximise this value, you maximise that value. What would happen if you could not, this question says, describe the motion of the car if the maximum velocity of the curve is exceeded. Well, we know what will happen. You fly off at a tangent. In other words, here is the curve normal, and if you're here, you will go in a straight line, or maybe hyperbolically, you might be able to go off like that, depending on how much friction there is. But you'll either fly off at a tangent or fly off at a curve less than the tangent. So, and you won't be able to complete the curve. So that's our description there. After you've done that, have a go at the compound question number 6. Please notice grams in this question, and this is a period, and that one there. So once you have periods, we need that this velocity is 2 pi r on d. Okay? Take a few moments now and do 5, 6, and 7, which is about the Earth's motion. Okay, off you go.